Welcome everybody. In this video we're going to introduce the concept of centripetal acceleration. We're going to use the letter AC for it, and that's the acceleration required by geometry for an object to be travelling in a circle at speed v or angular speed omega, where linear speed and angular speed are related by this relationship, where r is the radius of the circle. Now the way we're going to do this is a little different from what's in the textbook, because we're going to use what we learned from harmonic motion, because we derived an equation for harmonic motion, and we then explained it using a reference circle. So that same idea, which we got in chapter 4 of our textbook, Matter and Interactions, is summarized by this Python program, which we talked about a couple of weeks ago. So here's Bob, our mass on a spring, and he's bouncing backwards and forwards executing harmonic motion, and we could use the circle version of him to explain why we got a trig function for bouncing backwards and forwards, right? The thing that we got from solving the differential equation for harmonic motion. So let me just write that down so you can see what it looks like. Here's r, the position of Bob, right? So here's r, and it's going to be equal to a, the amplitude. So a is going to be the radius of the circle, and then we're going to write a vector, and it's going to be cosine of omega t, and then we need to do the y component of that, and I have another program which is a modification of the one you just saw, and I'm going to show you that. So basically here we've got the y component, and because he starts here at y equals 0, the trig function that goes with this harmonic motion on the y-axis is actually given by sine of omega t. And so this equation here is a parametric equation for r, because we're giving each of the components in terms of a function of time. Now the thing that we can do with this, because we've now got a function for r as a function of time, we can use the definitions of velocity and acceleration to see what acceleration there must be to be going in a circle. This circle, the one described by this parametric equation. So let's do that. V, the velocity, is defined to be the rate of change of position versus time. Pretty straightforward, right? So we've got this guy. The amplitude, we want to take the derivative of this. The amplitude is a constant, so it stays out the front. Omega, though, needs to come out by the chain rule, so we get 1 omega out the front. We get this. The derivative of cosine is minus sine omega t. The derivative of sine is cosine omega t, and we need to bring an omega out the front, but we already did that, so that's good. So this is our equation for the velocity as a function of time, and note that sine of 0 is 0, which means no velocity in the x direction, but the y component is positive because of cosine, right? Cosine of 0 is 1, so we get a velocity that goes up. Alright, so now that we have the velocity, because it's got an arrow on top, we can calculate the acceleration that goes with that, and that's by definition is just the rate of change of the velocity with respect to time. And again, taking the derivative of this, I get another omega out the front, so I get omega squared a, and the derivative of minus sine is minus cosine omega t, and the derivative of cosine is minus sine. And what you should notice when I look at this, so I've got two minuses here, so it'd be nice if I brought that out the front, so I can do that, and I get a equals minus omega squared a, and then cosine omega t sine omega t. And if you look really carefully at this, you should be able to see that this is the same as r, which means we can rewrite this equation as a, the acceleration for going around in a circle, is equal to minus of omega squared times r. And so that's the equation we were trying to derive. The centripetal acceleration, the acceleration for going in a circle, so let's put that in there to make it clear, right? I'm using the c here. This is our vector equation for a centripetal acceleration. acceleration, and it's the vector form of the equation. Okay, so that's actually pretty cool. So we just derived the centripetal acceleration, and this is quite a lot simpler than the one that we did, the one that's in the book, right, in chapter 5 of Matter and Interactions. So what I want to do now is just transform this into a slightly different version that you'll see, and that's useful in some problems. So let's talk about that. We want to rearrange this equation to solve for omega, and because we've got an omega squared here, let's just write out what that would be. Omega squared is equal to v squared over r squared. So if I substitute that in here, I get that AC, the magnitude of it, is equal to v squared over r. And this is the scalar form of the centripetal acceleration. Right, so let's just put that there, scalar form. And the scalar form, it's for the magnitude really. You need to remember when you're using this equation that the centripetal acceleration is always in towards the center of the circle. So what I'd like to do now is to do a really quick problem just to show you how this is used, because really there isn't any physics in this. This is just math and geometry. So let's do a physics problem that's related to Bob, and it's going to be this one. Find the v that Bob needs to have, the speed for Bob to travel in a circle on a spring. Right, so the exact problem that was in our Python program. And because this is a problem that has forces and accelerations and things in it, the correct way, the way that we've talked about a lot for how to do that, is we're going to start with a free body diagram of the object of interest, which is Bob. So let's draw Bob. Here's Bob. We're going to put him here. The force that's acting on him is caused by the spring, and we already talked about that. It's this way, F equals kr. That's the magnitude of it. And now what I'm going to do is I'm going to define the x direction in this way, the Beyonce direction, to the left, to the left. I know it's a bad joke, but it's one of the few I got. So the purpose of the free body diagram is to find f net. So here's f net. F net in the x direction, because we have our x going to the left, is kr. That's what I got from my free body diagram. And that's what we always do. There's no gravity in this problem, right? This version of the Python program did not have gravity in it. Then what we want to do is the same thing we always do, which is use Newton's second law to analyze the same situation. And that's F equals ma, and we're doing the x component here, and so we can write Newton 2 next to it to remind us of where it came from. But in this case, this formula, we know that Bob is traveling in a circle, right? And because he's traveling in a circle, we can use either one of these two equations for the acceleration. So I can write mac, which is equal to mv squared over r, and that's for circular motion. Right, so now we've recorded what we did, and if I combine these two lines, I get this, that mv squared over r is equal to kr, and the thing that we're looking for is v, so I can go v squared equals k over m r squared, and so I get that v, take the square root, is k over m square root of that quantity times r. And this is our answer to the problem. And just to show you how I did that in the program, let's have a look. This one, here is the velocity, the initial velocity of Bob, and you'll see that it's v equals k over m times a, which was our amplitude, because in the program I used r for the vector position of Bob. Alright, so we've now introduced centripetal acceleration, described what it is, and we've done a sample problem. Hopefully that'll help you with the homework that's assigned for this week. So let me just tell you where you can find this. Normally it'd be on D2L, but I'm going to post it on the internet for today, and it's going to be available as a PDF at my website, http://circle4.com/centripetal.pdf. Okay, so with that, hopefully you've got enough information to at least get you started on the homework problems for this week, and good luck with that. If you have any questions, don't hesitate to drop by and see me during my office hours, or ask in class.